Let's get started. Yes, welcome back. I'm Lisa Blackburn. This is my YouTube channel for everything I want to talk about science and math. And today we're finishing the chemistry notes, and we're going to do 2 units in one. Yay! Solutions and pH. So we're going to start with solutions. And so if you're in my chemistry class, these notes will be on Canvas and this video too. All right, so shh, everybody quiet. We're going to do this quickly. And remember that for your last test, these notes will be very helpful. So make sure you get everything down. So what is a solution? A solution is a mixture that has the same composition, color, and density, all the properties throughout. It is a mixture that has the same composition, color, density, and taste throughout. It is clear, generally not colorless. So our example is Kool-Aid. I think that's such a good little drawing of Kool-Aid. My son drew that, Joshua. He drew that one for me. So you can exempt, so make sure that I sign your paper. Okay. I gave you all of your bathroom passes, cookies, everything like that, and I pulled you up. So, yay! All right, so there's 2 kinds. It says the same throughout. Kool-Aid tastes the same if it's the first sip or the last sip of the glass. It's not like chocolate milk that settles out. It's the same throughout. Now, you can have, though, 2 different kinds of solutions that could settle out. And it's not really, but okay, so I'll have to take a little bit more time here. Okay, so technically there's one definition of solution, and it is this one. A mixture that has the same composition, color, and density throughout. It's clear, not colorless. That's the technical definition. But, and chemists will call solutions things that look like Kool-Aid. They can be different colors and they're clear. But then, and it's how it's normally used. But it's one of those words where we will use all the time just to stand for whatever is in that beaker. We'll say, go get that solution and bring it here. And it could be cloudy. It could be lumpy. It could have a copper wire in it. But we will just use that for whatever we are talking about that's in the beaker that we want to talk about at that minute. So this is one that's got a technical definition, but then it has a common use that doesn't always align. Does that make sense? Okay, so don't be confused. All right, so things that could be in the beaker could be homogeneous or heterogeneous. Now, you already have some prior knowledge. What does homo mean? Same. And hetero? Different. So homogeneous is the same throughout, like milk. Milk doesn't have a layer on top if you have homogenized milk, versus heterogeneous, it has layers. So our example of that is Italian salad dressing. That's not the kind that's all mixed up the same, but the kind that you have to shake first, that has the oil layer and the vinegar layer. Now, so here are 3 words that mean slightly different things in chemistry: solution, colloid, and suspension. A solution is clear, but not necessarily colorless. So Kool-Aid. A colloid is cloudy. And if we have time on Monday, we'll do a lab with that. And a suspension has chunks in it. That's your Italian salad dressing that you don't have to shake, but it's got little pepper flakes in it. It's chunky. Now, another part of learning about solutions is dissolving. A solute with a U in it is what gets dissolved. The solvent, and see how I made the V real big? I want you to draw little waves in it so you can remember. Imagine that's like a little cup of liquid there. You can color it blue. And it's got a little cup because the solvent is what does the dissolving. So like if you're making Kool-Aid, the water is the solvent, the Kool-Aid is the solute. Does that make sense to you? What gets dissolved is the oot, the solute. What does the dissolving is the solvent. A lot of you, especially if you're an artist and you have to thin your paint, you know about solvents. You know that word. Let's scroll up. Okay, I think I clicked some. Yep, and I scroll. Look at that. Look at that. Miss Olivier figured this out. She's brilliant. Okay. See if I can. Yep. Okay. So solvation is the attraction of a solvent with the ions of the solute. What this means is, what this means is that when dissolving happens, so here I have sodium chloride, and that's the balls right here, NaCl, NaCl, Na.
Ms. Blackburn,
Yes,
will you please send Evelyn Miller to the front office just for a moment?
I will.
Thank you.
Thank you. These are water. See how they look like Mickey Mouse or Kermit the Frog? Because the sodium and chloride have different charges, the sodium is positive. The negative oxygen on the water that is polar, it has a partial negative charge, will align with the positive because opposites attract, and it will pull it apart. When salt dissolves in water, it just doesn't fall apart naturally. It's attacked by the water, and it pulls it apart. So we got Mickey Mouse attacks, because these look like Mickey Mouse, and they attack it and pull it apart. Does that make sense to you? Okay, so dissociation is the separation of ionic compounds from one another. And an aqueous solution means it's been dissolved in water. And you already learned that when we did equilibrium. We talked about aqueous solutions, that they are involved in equilibrium constants. So if you're taking the final, it's cumulative. Couple of hundred fun chemistry questions on everything you've learned. Everybody who's exempting right now is going, yeah. But those of you who are going to do it, it's not bad. You'll do fine. Okay, so what can dissolve? So with the Kool-Aid, or say you're making sweet tea and you put sugar in it, you can have a solid like sugar dissolve in a liquid like tea. Okay, that's our first one. But also, you're familiar with Coca-Cola. And if you pour that Coke, bubbles come out. Those bubbles had been dissolved in the Coca-Cola. So you can dissolve a gas in liquid. Gas is dissolved in liquid. And so this is one thing. What do fish breathe? Fish do not breathe the oxygen in H2O. They breathe dissolved oxygen, O2, just like you do. Yes, Bryson?
What does it say in dissociation, like above that,
I can't hear you. You got to yell at me.
What does that say below solute, like dissociation?
One from one another.
Like just O-N-E?
O-N-E, one. You can put number one there, but it's not really the right one. Okay, so fish, through their gills, they take in water, they get the dissolved oxygen out of water. They do not breathe water. They breathe O2 just like you do. But it's O2 that's been dissolved in water. Also soda pop. Okay, but this is another one. They call it dissolving. And it's metal and metal. And what this is if you mix melted metals, you can get a mixture of metals like brass. Brass is not an element on the periodic table. Brass is a mixture of metals. So is bronze. They're not on the periodic table. They're made by mixing melted metal. That's hard to say. All right, we feel good about all that? So we got the one ring to rule them all there. I hope you realize that was from Mordor. Okay, now you probably already know about this because you're Southerners and you've had the terrible experience of ordering sweet tea up north and they bring you unsweet tea and a packet of sugar. And you pour the packet of sugar in the iced unsweet tea and stir and stir and stir, and will it ever dissolve? No, it's just like A snow globe. It won't dissolve. So what can speed up dissolving in liquids? Heat. You need to add that sugar to the tea before you put the ice in, right? So you need heat to help things speed up dissolving. What else can speed up dissolving? Anybody has bought, besides me, the little bitty, they're like little packets that are little long skinny packets, and you can buy them of Kool-Aid. Now they've got the ones that are Crystal Light. Crystal Light is not sugar, it's sugar substitute. So you put it in and it dissolves real easily. But you can take that little Kool-Aid one that's real sugar and put it in ice water and stir it up and it'll dissolve. What's the difference in why can you dissolve that little packet of Kool-Aid when you cannot dissolve the little packet of sugar at the restaurant in the unsweet tea? What's the difference in those two? Anybody ever had that? It kind of makes me want it just talking about it. I sort of want that Kool-Aid. It's really good. When we've gone to Florida, like to Disney and stuff, I didn't want my kids just drinking soda constantly, and I didn't want to pay $4 for every soda. And they let you bring food in, so I would get those little packets and take them in, and we would order the ice water for free and put it in and have it, and it was, you know, not all those bubbles and not all that syrup, and you felt better drinking it. But Florida water tastes bad, so we wouldn't drink just the regular water. And so thinking about those little packets, it makes me want to go to Walt Disney World and drink it in some ice water there. Makes me want to go Animal Kingdom. All right, so what's the difference? Anybody ever bought that besides me? Is that it's very, very fine. It's not regular sugar crystals. It's tiny, tiny, tiny pieces of sugar. So what is something that can speed up dissolving? Particle size, yes. The particle size. If it's smaller, it has a greater surface area per volume, and that makes it dissolve faster. So you can heat it up. You can break it down, and what's my third little hint there? You can stir it. It's a spoon. So when you get that sweet tea packet, you try it, right? You try to stir it, it just doesn't work. So the heat is better for that. Stirring. Okay, now how much can dissolve? This is vocabulary. So how much can dissolve at a given temperature is called the solubility. How much is dissolved is the concentration. I bet you already knew that from prior knowledge. No more can dissolve at that temperature is called saturated. I bet you already knew that word too, because like if you have a towel and you're mopping up a spill and it can't take any more, you say that towel is saturated, don't you? If more can dissolve, it's unsaturated. If more is dissolved that can dissolve at that temperature, it's called supersaturated. It's why we got Superman. I'll explain that a little bit more because I know that doesn't make sense. Okay, so how supersaturated works is you dissolve as much as possible with it heated up. And then really, really carefully, without bumping it, you cool it down. And if you do it real gentle and you don't bump it, you can get it cooler where more is dissolved at that temperature than normally would by heating it up and cooling it down, not bumping it. You can see videos of this on the internet. They'll have a solution and they'll hit it and it goes and it'll all come out of solution. That is the same. People will do this with water. It's not the same thing, but the result looks the same. You get a bottle of water right at freezing, and it will be water. You hit it, and it'll instantly freeze. Has anybody done it? It looks the same because it instantly freezes. I have a little thing I'll show you on Monday where you'll get to play with the supersaturated solution. Okay, so if something can dissolve, it's called soluble. If something cannot dissolve, it's called insoluble. If something can mix, it's called miscible. It's almost mixable, but it's miscible. If something cannot mix, it's called immiscible. It's almost mixable, but it's miscible. It's like it's got a s instead of. This is easy, isn't it? This is one of the easier things we've done. You already know a lot about this. Okay, and everybody got those words? May I scroll? Not quite yet. Like, I'll scroll just a little bit to get rid of the heat part. Oops. Okay, so in general, there is a thing we say in chemistry that like dissolves like. What this means is you know about polar and nonpolar molecules. Polar molecules are like water that have a positive and negative end. Nonpolar molecules are like oil that do not have a positive and negative end. They're sort of the same all around. So water and oil do not mix. But Kool-Aid can dissolve in water. That means Kool-Aid has positives and negatives. Does that make sense to you? What can dissolve in oil? Well, oil is things like, okay, so you've got a marker and it's a water-based marker, a Crayola that washes out. That would dissolve in water. But if you have a Sharpie, water doesn't take Sharpie out, but oil does. A dry cleaning fluid would take it out. One time I bought remember the lab we did where it was called rolling ionic, and we rolled dice to figure out cations and anions so we could learn to write ionic compounds. Remember that lab where we rolled the dice? Years ago, from a science catalog, I bought dice that were blank. They didn't have the dots on them, and you would write the anions and cations on the dice, so when you rolled it, it would have the cation and the anion, and you could do the same lab. So I was so excited about it. It said to write in Sharpie on the little dice, and I did, and I picked my anions and cations, passed them out, and as the kids were doing it, the letters started disappearing. And it was because the girls had lotion on their hands, probably some of the boys too. And the lotion the Sharpie is nonpolar, the lotion is nonpolar, like dissolves like, and they just came right off. Right off. It was such a disappointment. So that was not a good idea. So the dice that Miss Raymond, she thought of that lab with the rolling ionic. It was a much better one. So dry cleaning fluid. Dry cleaning is not dry. It's a liquid, but it is a non-polar liquid that can get out Sharpie, that can get out oil, that can get out body sweat, things like that on certain clothes. Okay, so what this means is polar can dissolve polar, like water and water-based markers. Nonpolar dissolves nonpolar. Sharpie and like Goof Off. Goof Off takes off like sticky stuff and oil and stuff. If you ever bought that, it's a chemical that does that. Okay, there are rules for solubility, and we already learned about this. NAGSAG. Remember NAGSAG? Our pig saying NAGSAG, and it's that soluble things are nitrates, acetates, group 1, the sulfates, ammonium, and group 17. So they have exceptions. The sulfates have exceptions, and the group 17 has exceptions. So remember that little chart. You might have a few questions where you'll have to use it again. And it says you have them in the back of your activity series in your notebook. So it's one of the handouts I've given to you. So precipitate is a solid forming in a liquid, generally in chemistry. Now on the weather, it's a liquid forming in the gas. If they say it's precipitation like today, it means it's raining. But it's really one state of matter forming in another one. What about hard water? Anybody been to Florida and like the water's weird, it smells weird, it's weird like when you try to wash your hair? Okay, that's hard water. and it has dissolved calcium, usually ions in it, and other salts that make it hard. Soft water doesn't. Now, hard water can cause problems. It makes soaps not clean good. It leaves deposits, mineral deposits in your potty, on your bathtub. You get soap scum. It's just a pain. Hard water is a pain.
Is that in cats?
That says calcium ions, Ca+2.
Oh.
And it is a cation. So soft. One of the what's wrong with hard water? Soaps and detergents don't lather well. I left off the R there. They don't lather well, and it makes soap scum build up. And you're like, well, that's not that big of a problem. Soap scum, yeah, you have to scrub your bathtub, but the problem is pipes. If you have soap scum, it'll build up in your pipes under your house where the bath water and the sink water goes, and it gets smaller and smaller and smaller, and then it causes plumbing problems in older houses. So that's the problem, is that soap scum that will build up in it. And that, it can be a real pain, clogging up plumbing. All right, may I scroll up? We good? Okay. So this is the problem. It makes minerals build up in pipes, radiators, tea kettles. It causes things to tear up. It makes minerals build up. Build up. Okay, now more about concentration. Concentration in chemistry can be described in different ways because there's different kind of chemists. There's me, a high school chemistry teacher, and I generally have concentration one way. But say you're a chemical plant making tons of chemicals. A lot of times they make their concentrations and express them differently. So there's different ways to do this. One way is mass percent. It's the mass of solute divided by the mass of solvent times 100. I don't usually use that in chemistry. What we do in high school is this one. That's why I got little stars. This is what I use. I use molarity. Remember when we did that experiment where we put 3M and 6M hydrochloric acid on, what did we put it on? Zinc to make it bubble, and the 6 molar did better. Do y'all remember doing that? And there were little droppers, and some said 3M and some said 6M. That 3M and 6M tells you the concentration, and the 6M is more concentrated. It's stronger. So molarity is the moles of solute divided by liters of solution. The units are moles, written big M, so the symbol is written in square brackets. So you put square brackets around the concentration and then a big M. And that's what we do in chemistry class. Now in industry, they use molality more. And that's moles of solute divided by kilograms of solvent. They weigh out their chemicals when they make them. It's used in industry more, and its symbol is little m. There's an old way with acid called normality. You take the molarity times the number of hydrogens in the acids that come off water. You will learn more about that in college. I don't use that much, and there was a bottle of acetic acid that had normality on it back there, and I was like, oh, I have to remember that and figure out what that means in molarity. It taxed my brain, but I figured it out. It was actually really easy once I thought about it. So, in common speech, how we talk about concentration is we will call things concentrated or dilute if it's watered down. So you need to know that word too. So here's an example math problem for concentration. What's the molarity of the solution that has 10 grams of sodium hydroxide dissolved in 100 milliliters of water in a volumetric flask? Well, first you have to get the molar mass of sodium hydroxide off the periodic table. 23 plus 16 plus 1, which is 40, and that's grams per mole is our unit there. we have 10 grams of sodium hydroxide, and we're going to figure out the molarity. We're going to put, what we have is 10 grams per 100 milliliters. We're going to convert the grams to moles by dividing by 40 grams. And 40 grams is 1 mole. And then we need to change those milliliters to liters. And 1,000 milliliters equals 1 liter. Grams cancel out. Milliliters cancel out, and I'm left with moles over liters, which is what I want. So it's 2.5 big M in square brackets. 2.5 molar. Okay? That math seem doable? It's just a conversion factor that we learned our first week in class. How to do conversion factors. All right, the next thing we have to do is to be able to read a solubility curve. And I ran one off for you, but it's so light, it's kind of hard to see. But what you do is you look at, on one side, you look and see how much dissolves in water. And on the other side is temperature. So if I want to see how much potassium chloride dissolves at 40 degrees. I go up, straight up from 40, hit the line, then go over, and I can see that it's a little less than 40 grams would dissolve in the water. So that's how you use that chart, and you'll get practice with that. Now, what improves, we talked about what improves dissolving a solid in liquid. It was heat, particle size, and stirring. But what about Coke? What if you go work for Coca-Cola and it's your job to get the carbon dioxide bubbles in the Coke? Do you think it will help do that if we heat it up, stir it, and have smaller particle size? No, not at all. Anybody been sick and your doctor tells your mom to give you ginger ale or Sprite, but to stir it first? Why does the doctor tell you to stir it first? To get the bubbles out. So, but stirring Coke makes the bubbles come out. So what improves dissolving? Pressure. That's why when you open the Coke, it goes because it's letting off the pressure. And cold. A cold Coke will stay fizzy longer than a hot Coke. You're out at the pool, it's summertime, you got your Coca-Cola there, it's in hot Georgia sunshine, it's going to go flat really fast. Have y'all noticed that before? That they go flat a lot faster? Okay, so for example, soda, beer, champagne, sparkling water like Perrier all have carbon dioxide dissolved in it, or and you'll also see it as carbonic acid, which provides that same dissolved gas. Particles in solution. When ionic solids dissolve, they become charged ions. Charged ions in solution and can conduct electricity. For example, salt water versus non-electrolyte sugar and water. Now I got a little lightning bolt here. Do I have it here or on the next page? Let's see how we get. Oh, it's on the next page. I'm getting ahead of myself. Can I scroll?
Yeah.
All right. So when you have dissolved cations and anions in a solution that they disassociate and are floating around charged, it's called an electrolyte. There's a REM song called Electrolyte that I always want to sing when I get to this. Electrolyte. But here I've got a symbol. What logo is that? Gatorade. Okay, so Gatorade, if you drink a lot of water really, really fast, then you'll throw up. You'll barf. The reason why is because your body, remember I always tell you nature likes balance? And remember in biology when you learned about osmosis and you learned hypertonic, hypotonic, isotonic, remember those words? What it means is that you have a certain salinity to your body. Your tears are salty. Your spit's a little bit salty. You're got a certain amount of salt in you. If you drink a bunch of pure water, then your body will try to have balance and try to balance out the saltiness of the water in your stomach and the water in the salt in the rest of you. And it's just too much to deal with if your body is very hot and exercising and sweating. So instead your body will just barf and you'll throw up. When I was a college cheerleader and we were required to take weight training because we had to be able to lift our body weight because we would build pyramids and you had to be able to pick up someone at least as heavy as you and lift them over your head. So we had to do weight training. On the first day of weight training in college, all these guys were in there who lifted, and then they guzzled down water and went out in the hall and threw up in the trash can. Now, I guess I didn't try as hard as all of them because I didn't throw up, but most people did. If they had Gatorade, they probably wouldn't have thrown up because Gatorade was developed by the University of Florida Gators. I know, but people in Georgia drink it too. And it's the same salinity. It's salty. It's not just sweet, it's salty. So you can chug it. You can be really, really hot, really, really thirsty, and you can just put your head back and drink a whole thing at once, and you won't throw up. And it's an electrolyte. So would Gatorade conduct electricity? Yes, absolutely. Yes, it would. Okay, so there are other examples of things that conduct electricity, solutions to electricity, inside of batteries or chemicals. And also you can make a battery with chemicals, liquid chemicals, electrolytes, and that's something we would do in AP Chem. So sign up for it next year after you've done your physics. Now, and we will talk more about that in the next notes, okay? Okay, so in general, when you add solute particles, it causes changes in the solution. So if you add salt, it will cause a rise in boiling point. Boiling point will go up. So when you add salt to the water to boil spaghetti, it means that it goes a little above that 100 degrees Celsius that pure water boils at. It boils a little hotter. It also lowers freezing point. It causes freezing point to go down. That's why they put salt on the roads if it's going to be freezing and raining and they want to make sure people don't slip their cars off the road, they'll come out and salt them. We used to not do that in the South. They used to do it up north. But because we only get snow on average, according to the weather, once every 2 years, they didn't bother buying the salt in the salt trucks. But then, and if it snowed, everybody just stayed home and didn't worry about it. Well, then we've had some problems with that, haven't we? With kids getting stuck at school. Did any of y'all get stuck at school a few years ago with the big snow? So that's a problem. So, and too many wrecks. And the city of Atlanta is a big city to just everybody decide to stay home. So now we've got salt trucks and like they do up north. We're all fancy. The other thing is the vapor pressure will also be lower if you add salt to it. Now there's another thing where you can calculate this. There are formulas that go with this. I'll write it. The change in temperature, oops, I did that upside down because I'm dyslexic. We'll make it capital B. Equals KB M. So there's a constant called the boiling constant, and you multiply it times the molality, and you can figure out how much these things shift. You can also do the same thing with the freezing, and it's the same formula. It's a constant times the molality, the freezing constant. So this is a little formula. I don't think it's on your test, but if it is, I will give you 2 of the 3 things and you solve for the other one. Very simple problem. So here's another thing you might know about. Anybody made homemade ice cream? You add rock salt to the ice in homemade ice cream, and it will make the regular freezing point of water, 0 degrees Celsius, go to -2. It makes it colder than freezing, and it helps that ice cream freeze. Colligative properties is what this has to do with. These are properties that a chemical has, or a solution has, that's based on the number of particles in the solution, not the type. For example, this change of boiling point and freezing point, if you add salt to a road and it's 32 degrees Fahrenheit, the road won't freeze where you add the salt. It doesn't matter if you add and how much salt you add depends, is going to change that. More salt, more property. If you go in your driveway with the salt shaker and go, it probably isn't going to help. It takes a lot, right? They really put a lot there. Okay, now all of this has to do with polarity. And you have to remember that polar has charged ends with molecules like water. Water is the great example of a polar molecule. Non-polar doesn't have charged ends like oil. And soap, what's great about soap is it's both. It's sort of like a fish hook, where it's got one end that is non-polar, and it will stick in oil. It has another end that's polar. Water comes along, will grab the polar end and pull it off. So I used to always teach people, so soap doesn't work without water, and water doesn't work without soap, and that's why your mom told you to use soap and water when you take a bath. Then I had this girl come up to me after class, and she said, Miss Blackburn, I never use soap. Does that mean I'm dirty? Do I stink? And I started thinking about it. Okay, she didn't stink. She didn't look dirty. So why? Why did the chemistry not work? Why is it that she could put water on and be clean? Well, the thing is you can actually not use soap, and you can clean with oil. You can clean with oil. You can, people will use their iron skillets and they will not put soap on the iron skillet. Instead, they'll clean it with oil and salt. And you can clean with oil. Because like dissolves like, you can use oil to clean instead of water. Does that make sense? So like she used oil. She actually was able to be clean with oil. She would wash with conditioner instead of soap. And it worked. And she was clean. And the reason why she never used soap is because she had really bad eczema. Eczema is just this allergic reaction that causes you to have super dry skin where it'll like split and bleed and scar. I knew a little girl once who got it, who she ended up getting staph infection in it, and it was life-threatening. She ended up in the hospital. She ended up at Scottish Rite. So eczema can be very serious. So I always kind of want to tell that because I don't want people to think, oh, I don't use soap and maybe I should, especially if they have eczema. Maybe they shouldn't. All right, so let's go on to acids and bases. Try our next one. Let's see if I can get it here. It should be right there. Oh, look at this. We are doing so good. Yay, Miss Olivier. Okay, you already know a lot about acids and bases, so this shouldn't take too long. So pH, acid, and bases. pH tells how acidic or basic something is. We have 2 formulas here for pH and POH. So this is fun because we get to use that button on the calculator that says log. Haven't you always wanted to use all the buttons on your calculator? And so we get to do some problems where we use it. So to get the pH, it's the negative log of the concentration of hydrogen ions in something. To get the POH, which is sort of like pH, but we use it sometimes in chemistry, is you do the negative log of the concentration of hydroxide. Remember the polyatomic ion hydroxide? And so if you see the little square brackets for concentration, it gives you a number. If you add pH plus POH is 14. So this number, when we usually just use pH, tells you how acidic or basic something is. I bet all of you already knew everything I just said except the formulas, right? You already know this a little bit. So acids, how do they taste? Sour or bitter? Sour. Because a lemon is, oops, I gotta do this again. I got to draw, I gotta pick a color. Okay, they taste sour. So our lemon is an example of something that's acidic. What this is a long time ago, Kool-Aid used to have a competitor. And this was where, like how Kool-Aid Man is the Kool-Aid symbol. These little funny fruits were the ones for the competitor. So I decided to draw them. Okay, so what makes an acid is it has hydrogen ions dissociated in the water, and this is the Arrhenius definition. Now, remember when we started talking about gases, I said that gases, it was one of the first things we learned, so there's all these different units for pressure. Well, we knew about acid and base long before we knew chemistry. People going all the way back tasted of a lemon and said it was sour, right? And then they would say, oh, that's acidic. So we knew what these things were before we ever knew about chemistry. So therefore, there's a lot of different definitions of what's an acid and what's a base. The word acid and base goes way back further than chemistry. So therefore, there's different definitions. You'll learn more in AP chemistry or college. Okay? So that's one definition. Another one is the Bronsted-Lowry definition, and that is an acid donates a proton, which if you had a hydrogen is only one proton and one electron. If it loses its electron, it's a proton. So you see our proton H+, so there's very similar definitions, okay? This is another thing where there's a reaction. HCl is hydrochloric acid. H2O is water, but here the acid is going to come apart, the hydrogen and the chloride, so it's going to donate a proton. The water is going to accept the proton and become H3O. So it is going to, even what it is not, water is neutral, it acts like a base. It's not a base, but it acts like one because it accepted it. This one is what accepted the proton. It's called the conjugate acid. Conjugate acid, and if you can't read these, don't worry about too much. And the chloride is the conjugate base. And we're not really going to go into that too much, but you can have it in your notes. You can figure it out more if you want to. Okay, another thing that is said to make something an acid is it has the hydronium ion. And the which is this H3O, that's called the hydronium ion. So that's what I want you to do is draw a little arrow to that. H3O. So that would make it acidic, yes. This one says conjugate acid, conjugate base, and here our water is acting like a base. Acting like a base. But this is not very important. I don't want to spend much time on that. You'll learn more about that in AP when you come back. It will be great fun. We'll have a great time. I have all that fun lab equipment in that prep room that I don't get to use because nobody's taking AP. So I got to come back and play, and we'll get out all the fun equipment that's back there. Okay, so what do acids react with? What kind of music is this guitar? Heavy metal. So acids react with metal, not with the music, but with actual metal. That's why we put hydrochloric on zinc. And this little piece of paper, you need to color this part blue. Let me do it too. You need to color this part blue. Oops, I got too excited there. That'll do. And The other part on the end needs to be pink. Let me go back to red there. All right, so if you have a piece of blue litmus paper, it will turn pink if you put it in the acid. So, but they call it red. They say they're calling it red, but it's really pink. So an example, what is an example of acid? We'll say lemon. And we're going to learn more in lab on Monday. Bases taste bitter. Now, there's a little bitter like soap, okay? Not bitter like coffee. Coffee is actually an acid. So don't let that confuse you. Bitter like soap. Anybody got caught cussing and your mom made you put soap in your mouth like Christmas Story where he has to eat Lifebuoy? My mom didn't do that. I never had to have the Lifebuoy in my mouth. Okay, let's see, can I scroll it here? Oh, I can. Look at that. Okay, so what makes something a base is that has hydroxide ions. That's the Arrhenius definition. So here we have sodium hydroxide, a base, and it breaks into sodium and hydroxide and water, so it's a base. They also, you can say, it accepts a proton. That's the Bronsted-Lowry definition, because ammonia is also a base, and it has that unshared pair on the nitrogen where it can have extra H. It can accept a proton and become NH4. So bases are soap. So how do bases feel? How does soap feel? Slick, right? Slippery. They feel slippery. They react with fat. That's how you make soap. Is you mix a base and fat, and it turns red litmus blue. So on this one, color it pink with blue on the end. The pH of a base is 7.1 to 14. The pH of an acid is 0 to 6.9. So an example of a base would be ammonia, lye, like lye soap, lye. Now the strength, these acids and bases can be strong or weak, okay? So for strong acids versus weak acids, they disassociate completely in water. They disassociate completely in water. Can I scroll it up to there? So they are more dangerous than weak acids. So hydrochloric acid is more dangerous than lemon juice. And they also have a very low pH if they're strong. So examples of strong acid is sulfuric acid, that's battery acid. Hydrochloric acid, that's your stomach acid. Nitric acid, perchloric acid, those are all very strong acids. So we have HCl, it's a strong acid. Strong acid, hydrochloric acid. Now weak acids are things like vinegar, acetic acid, citric acid, lactic acid, and milk, and they do not disassociate completely. So that is a weak acid right there. Weak acid. Now, strong bases versus weak bases, they, once again, disassociate completely. And they are also more dangerous than weak bases. They have a high pH. The higher the pH, the stronger the base. So that's sodium hydroxide, and it's a strong base. So Drano would be a strong base. That's all bases there. That's an acid symbol right there. There's your battery. All right, I want to scroll this up again. Can I scroll? No, can I scroll a little bit? Can I scroll to there? No? All right. So this is a strong base. That's lye. And that's the strong base right there. So examples of strong bases: lye, sodium hydroxide, potassium hydroxide, barium hydroxide. How can you tell? How do you tell with the pH of something? We do that with an indicator. And we're going to look at that in lab on Monday. So you can have litmus paper, universal indicator. We've used that one. Phenolphthalein, you've used that one. Hydrion papers, you haven't used it yet. Now, what do you think happens if you mix a really strong acid like hydrochloric acid and a really strong base like sodium hydroxide together? What do you think would happen? What? What'd you say? Nothing. I always want people to say, "Oh, blow up. It's a bomb." Nope. And they cancel each other out. Hunter was right. What they do is you get salt, a salt, not always sodium chloride, and water. That's why we got the little fella on the beach. You get salt water. So here's hydrochloric acid plus sodium hydroxide makes water and salt water. Okay, so quick little aside with that. So there is, in certain cultures that used to not be here, that's getting to be more prevalent here, where what they do in their culture is, if historically, is if a guy asks a girl to court, to date him or whatever, and she rejects him, that they will do a thing where they will throw a really strong chemical and try to kill her and melt her face. Yes, it's called an acid attack. You can see pictures of it on the internet. I wouldn't advise it. It's very disturbing. So that used to just be in what we would consider developing nations, but some of them aren't developing, or third world countries. Okay, it's a different culture than ours that considers this okay to do. But because things are changing here, it's starting to happen more here. When I taught in Cobb County, there was a lady who, it happened to her, and someone attacked her with a chemical like that. And last winter it happened, I think, in Chicago or New York, and it happened to a stranger. So it's starting to happen not just if someone asks you out and you say no. It's starting to be a form of terror attack. Okay, this is terrorism. It's coming more to our country. So what about if that happened to you? Well, this lady was, 50 years old. She had walked out of her house to go walk her dog, and so a complete stranger attacked her in a terror attack and threw a chemical on her face. She did make it to the hospital and live. It melted her face. She's blind. Her face is gone. Okay, she is disfigured for the rest of her life. If that happened and you were there, what should you do, knowing what you know about chemistry? What should you do first? What should you figure out? If it's an acid or a base. So if we're not going to, you might taste it. We're not going to think about sour. We're going to think about feel. Doesn't feel like water, it's an acid. It doesn't feel slippery like soap, it's a base. So now you know which one it is. What do? It's usually a base. It's usually slippery. Okay, so it feels slippery. What do? You're the lady or her husband or her kid, and you're right outside her house. What do you do as you're dialing 911? But the ambulance is not going to get there in time to save this person. You've got to act. What are you going to do?
Spray with a water hose.
Yes, vinegar. You go run to the kitchen and look for vinegar. Look for a Coca-Cola. Look for a mild acid. Now, we're not going to get the bottle of muriatic acid, which is hydrochloric. We're not going straight for the strong acid. We're going to go get vinegar or Coke or a Diet Coke and pour it on her face as quick as you can. And then what about if it feels like water and it was an acid? What are you going to go get? What's in your house? What's in your house you can put on it? What? Soap. Or I'd go for ammonia. If you got ammonia, make sure it's ammonia and not more acid. But I'd go for a cleaner and pour it on them as fast as you could. You might save their eyesight. Yes. Yes, Windex. Windex. May you never have to have this knowledge, but if someone had had that knowledge last winter, they might could have saved her sight in her face. So it's a terrible world we live in. Y'all have to know some things. Y'all have to have a plan to defend yourself. So, if I can help, I want to. All right, so what about water? What about water? Water is neutral. It's neither an acid or a base, but it can act like an acid or a base, and it's actually made out of an acid and a base. It's made of both. Water is H2O. It's made out of the proton, the hydrogen proton, and the hydroxide. It's made out of an acid and a base. And it's both. So the pH of water is 7, and it is not acid or basic, it is neutral. Now, how do we do the math? You calculate pH of pOH is reported on the pH scale. That number is called the pH scale, and this is how you do the math. So get out your calculator. We got just a minute. We'll try one, and then you can try the others yourself. What you're going to do is you're going to take the negative log of that number. So on your calculator, hit negative log and then put in 0.235, and you should get 1.6 is the pH. So try to take the negative log of that number. Sometimes the log is written in scientific notation.
Where's the log?
Log, it should say log on the side. If you have one of the TI-84s, log is right there. If you have the TI-84, it's right there. So if you're going to put this in, I'm going to do negative log, and then I'm going to put 0.0235, enter, and there it is, 1.6. So this is a strong acid. That's something like hydrochloric. All right, so I'm going to let you try those.
I keep getting 3.7.
Okay. That's a setting on your calculator, and we can fix it. Okay, so we'll talk about that on Monday. We'll get the worksheet on Monday. So the other thing you have to know is pH plus pOH is 14. So if pH is 3, pOH is 11. Why aren't we drawing? So 3 plus 11 is 14. If pH is 10, what's pOH? 4. If pOH is 8, what's pH? 6. So the last thing you have to know, 1 minute for the last thing. There is a thing called electrochemistry and redox reactions. What I want you to know is this assignment. Leo the lion says grr. There's Leo, he's saying grr. And what that means is when a chemical loses electrons, it's called oxidation. You need these last two words. And the gain of electron is called reduction. The gain of electrons is reduction. All right, so we almost made it. We'll talk about Leo the lion on Monday, and we'll do our labs. Science is great.